I hope you've had a chance to play around with the applet that showed the graph of b to the x and its inverse function log base b of x, and that you were able to conclude that the graph of the inverse, as we discussed last week, is the graph of the original function reflected around the line y equals x. So this tells us, like we were saying in the last problem, that since the range of b to the x is positive, therefore the domain of its inverse, log base b of x, is also only positive numbers. So there's nothing happening with the graph of log base b of x when x is not positive. When x is 0 or when x is negative, we're not allowed to put those numbers into log base b of x. Another thing that we talked about last time excuse me, was that how the inverse function and the original function undo one another. So we expect that the answers to these should be x. If I take a number and I put it into the exponential function, and then I take that answer and I put it into the log function, they should cancel each other out. And the same thing down here. If I put a number and take a number and I put it into the log function, and then take that answer and put it into the exponential, they should also cancel each other out, except we said we have to be careful last week that the x's that we're plugging in are legal things to plug in to these inside functions. So what is the actual domain of the exponential function? Are we allowed to put in all real value x's into a function like 2 to the x or 10 to the x? And the answer to that is yes. I can put in negative x's, I can put in 0 for x, and I can put in positive values for x, as we discussed last week. So this is really true for all x. Now, is the same thing true here? What did we just say about the things that we can legally put into the log function? Those are the things that legally come out of the exponential function. And as we said, if the range of the exponential function is positive x, therefore the domain of the log function is also positive x. So this is only true for all x greater than 0. We're not allowed to put in 0 for x, and we're not allowed to put in a negative number. Just as we had last week some very useful exponential rules, we have 3 useful log rules that really just come from the fact that the log is the inverse of the exponential function. So for example, not for example, we're going to do all 3, but the log base b of x times y is what? You can always pause your tape here and at any time give yourself a chance to decide if you know what the answer is instead of just listening to me tell it, so that you're feeling like that you are actively participating here. The nice thing about the log function is that it takes multiplication and it turns it into what? It turns it into addition. And probably none of us, including me, has ever used a slide rule, but as I understand things, this was one of the principles that made slide rules work so well, is that they turn something difficult, like multiplication, into something easier, namely addition. Similarly, the log will turn a quotient, division, and again, division is something that's hard to do, especially if you're dealing with big numbers, into something that's easier to do, namely subtraction. And for our purposes, the most useful property is going to be this third one, because remember, we're interested in solving equations like this one. This was the example that I gave at the start of the day, 5 times 3 to the x equals 19. Somehow I need to get this x out of the exponent. And that's exactly what this third log rule does. It says that if I have log base b of x to the y, in other words, if I have this really hard operation called exponentiation, I can turn exponentiation into something that is easier, multiplication. So these are our 3 log rules. And you should not try to invent your own log rules, even though it is very tempting, and I've seen people do it a lot on exams and homework. For example, there is no rule here that has an x plus y in the log. And that's because there is no rule for that. Similarly, there's no rule here that is an x minus y. We get a plus outside of the logs, and we get a minus outside of the logs. But there was never a rule over here that said the log base b of the quantity x plus y or of the quantity x minus y. So even though it might be tempting to think that you know some rule for that, there is no rule. And it's not just that we haven't figured it out yet. There simply is not a rule for that. Let's use these log rules to try to help us solve some equations. So this is the one we started with, 5 times 3 to the x. And you might have your own strategy. There's more than one ways to do these. I'm obviously only going to write one on the board. Somehow we need to get this x out of the exponent. Our first choice could either be to divide the 5 to the other side, or I could take a log right away. To me, it seems a little cleaner to divide the 5 to the other side. So I will get 3 to the x equals 19 over 5. And then I want to get the x out of the exponent. So I can take the log of both sides. And I can use any base that I want. Doesn't really matter. If the question actually asks me to do something like give it correct to 3 decimal places, as the questions sometimes do on homework and exams, then you'd like to use a button, a base that actually appears on your calculator, meaning probably base 10 or base e. I am always going to use base e, natural log, because as we're going to find out later, it is the most natural of them, and also it involves simply writing the fewest number of characters. So I'm just going to take ln of 3 to the x. And often what I'll see on homework sometimes is people will just write that. And then they'll proceed to do their log rule, bring the x out front, and solve. But was this really legal? I had two things that were equal here, and I applied a function to the left side. I've got to apply the same function to the right side, otherwise this equality is not going to be maintained. Meaning now I have ln of 19/5. Now we can use our third log rule, bring that x out front. So we get x ln 3 equals ln of 19/5. And you notice that, as we always want, we want exact answers unless we're told otherwise. So we are resisting any thought about getting out a calculator and putting in 1.09, whatever it is, for natural log of 3, because your calculator is not possibly going to give you all of the correct decimal places. They're infinite. They go on forever. They never repeat. You have no hope of trying to write them all down. This symbol here, ln of 3, gives us all of them perfectly. And then our last step is just to divide. X equals ln of 19/5 over ln of 3. And that's our exact answer. And if you wanted to get a calculator approximation to it, you could go ahead and do that. Let's try this one. So this time, just for the sake of variety, let's not combine the two terms into one. Let's just take a log right at the very start. I'm again going to use natural log. If you want to use a different base, that's fine. And now what rule are we going to have to use next of our 3 log rules? Rule 1 or rule 3? You might be tempted to bring this 3 to the x all the way out front, but we can't do that by rule 3 yet, because I still have a product here of 2 times e to the 3x. So really, first, we've got to use rule number 1. So we'll get ln of 2 plus ln of e to the 3x. We've got to do the same thing on the other side, right? Because order of operations says we do exponents first. So what's being raised to the 3x power here is just the e. It says we do the exponent and then we multiply by the 2. If I wanted to raise all of this stuff to the 3x, I would have needed to put the 2e in parentheses. But it's not in parentheses, and we cannot just insert parentheses wherever we feel like it. So we've got to do the same rule on this side. ln of pi plus ln of 7 to the x. Now we can use our exponent rule and bring those x's down. ln of 2, 3x comes out front. ln of e. And you can leave ln of e in there if you want, but ln of e is saying find the exponent to which I raise e to get e. So what exponent do you raise e to get e? That's just 1. So this is just the number 1. And here we have ln of pi plus x ln of 7. And this might look like some terribly nasty equation, but what kind of equation is it actually? This is just a linear equation, because ln of 2 is a constant. I have 3 times x to the first power. ln of pi is a constant, and x times ln of 7. ln of 7 is another constant, maybe not a very nice constant, but it's a constant. So here we don't have x to any power other than 1, so it's just a linear equation. So you should ask yourself, what's your general strategy for solving a linear equation? And probably you would say something like, I want to start off by getting all the x's on one side. So let's leave the 3x on this side. And let's bring this other stuff to that side, x ln 7. And let's get everything else onto the other side. Now we're almost done. Now we've got two different x's here. We wish we only had one x. And we can accomplish that by factoring an x out of both of those two terms. So we get x. When I factor an x out of the first one, I'm left with a 3 and an ln of 7 from the other one. And on this other side, I have ln of pi minus ln of 2. And then the last step is just to divide by this 3 minus ln 7. And again, this is our perfect exact answer. There's no rounding that's been done, no estimation at all. And you can see that, for example, we could combine the ln of pi and the ln of 2 by using our second rule backwards and combine that together and just get ln of pi over 2, which is what would have happened if you had, instead of what I did and taking the log right away, if I had first divided both sides by 2, I would have gotten a pi over 2 on this side, and then I would have taken ln of pi over 2 there, which, as we just said, is the same as ln of pi minus ln of 2 by our second exponent rule, our log rule. Let's try a few more. So there we were focusing on solving equations where we had an exponential function and we took the log to get rid of the exponential function. Now it's the other way around. We've got an ln function here. We'd like to get rid of the ln. So we need to do the inverse of the ln function, but the inverse of a log function is the exponential function as we defined. So I need to do what's called exponentiate each side here. I want to take e to the ln of this. You know, if a equals b, then e to the a must be the same as e to the b. But because we cleverly chose e as our base here instead of 3 or 10 or something else, the e to the x function and the ln function cancel each other out because they're inverses. This just becomes x minus 4 equals e to the 5, or x equals 4 plus e to the 5. And again, this is the exact answer. There's no way you're going to get all the decimal places for e to the 5 out of your calculator. So just leave it like this unless it specifically says that we want 3 decimal places or something like that. All right, here's another function that's got exponents. Should we be using logs to try to solve for this equation? And the answer is no, because we don't have any variables in the exponents. We have actual numbers as the exponents. So these are power functions, not exponential functions. So we do not want to be doing anything with logs here. So there's now two approaches that people most commonly take with this. They either factor or they divide. You might say, oh, I want to can divide x to the 4th from each side and then solve. Or you might say you can factor. Let's try both. So first let's factor. So I can factor out of each of these terms an x to the 4th. And I'm going to be left with an x squared minus 5. And one wonderful property of the real numbers is that if you have two real numbers that are multiplied together, one of those has to be 0. You can try all your life to find two non-zero real numbers and multiply them together and get 0, and you will never succeed. And this is a very useful and very powerful property of the real number system. It's not true about all number systems. There are other number systems where this doesn't happen. But luckily for us, we're working in the reals. So if I have these two things multiplied together, either x to the 4th must be 0, or x squared minus 5 must be 0. So now you have to ask yourself, what is the number which, when I raise it to the 4th power, gives me 0? And that number is 0. Or if I were to move the 5 to the other side, I'd get x squared equals 5. So does that mean x equals the square root of 5? I think we looked at an example like this last week where we had something like x squared equals 9. And we said that when you're solving an equation like this, you'll get two solutions. because I could have had the square root of 5 being squared or the negative square root of 5 being squared. So there are actually two solutions to x squared minus 5 equals 0. So factoring, we got three different solutions. What if we tried dividing? So how about as an alternate solution? Alternate method, let's call it. I start with my x to the 6th minus 5x to the 4th equals 0. And maybe you first move something to the other side, 5x to the 4th. Oops, we're going to divide by x to the 4th. Or you could have divided by x to the 4th already. But when we now go ahead and divide by x to the 4th, what do we get? We get x squared equals 5, and that's an equation we're already good at solving. And we get x equals plus or minus the square root of 5. So what happened when we divided? We know that there's supposed to be three solutions, right? X equals 0 definitely solves this equation because it makes both sides equal 0. But when I divided, I lost that solution of x equals 0. So it's very dangerous to divide. Whenever you can factor, you should factor. So we lost the x equals 0 solution. So I'm just going to cross off this method altogether and say it is very dangerous to divide. You should not divide unless you are absolutely forced to divide. Factoring is the way to go. We will be seeing many, many equations this semester of the form something over here equals 0. And we will see again and again and again that factoring will allow us to find all the solutions, whereas if we divide, we run the risk of losing one solution. And in theory, this is what your algebra teacher told you when you learned algebra, that if you divide by something, you're supposed to check if that thing being 0 solves your equation. And if it does, then you're supposed to go ahead and remember that and say that that's a solution of your equation. Because if x to the 4th was 0 here, we technically divided by 0, which was illegal algebra, right? We're not supposed to do that. We're supposed to check that case separately. All right, let's try this one now. Here we do have exponential functions. I've got an e to the x on both sides. So should I first take the log of both sides? Would that be a good idea? What would we be doing on the right side? We'd be taking the log of 0. Are we allowed to take the log of 0? We've already said tonight that that is not allowed. You can only put positive numbers into logs. So we can't do that. You might be tempted to move one of these terms to the other side and then take the log. But again, as soon as you take the log of something, you are assuming that that quantity cannot be 0 and cannot be negative, meaning if there are solutions that make those quantities 0 or negative, you're going to miss those solutions. So again, this is not an example of trying to move things to the other side and take logs. This is another example of factoring. So let's see what we can factor out. Both terms have an e to the x in them. So if I factor out an e to the x, I get a 3 to the x from here and an x cubed from here, still being 0. But then you might say even this can be factored further. So now I can factor out, what can I factor out of both of those terms? I can factor an x. So e to the x times 3 plus x squared equals 0. So now we have three quantities multiplied together that are equaling 0. And if over the reals, that can only happen if one of those quantities is 0. So that must be either e to the x is 0, or x is 0, or 3 plus x squared is 0. We really want you to know this thing about e to the x being 0, huh? This is the third time it's come up. We couldn't take the log of 0 earlier today in the first video segment. We decided over here that taking the log of 0 would be bad here. And the reason we can't take the log of 0 is because there is no value of x that will make this happen. So e to the x can never be 0. That has no solution. If you graph e to the x, you're always above the x-axis, as we spoke about earlier. Well, the solution to x equals 0 is, of course, x equals 0. And can 3 plus x squared ever be 0? If you tried to get the x squared by itself, that'd be saying x squared equals negative 3. And there's no real number that when you square it will give you a negative. And we're not going to work with imaginary numbers until a special treat the very last week. So this one also has no solution. So the only solution to this was x equals 0. So I hope the moral of the story for part D and part E is that it's safe to factor and it can be dangerous to divide or just take the log without considering what sort of solutions you're missing. So these problems were intended to help us just get used to using logs to solve equations and also not to jump into using logs when they're not necessary. But as we've talked about last time, we also want to be able to solve word problems and apply our functions. So suppose that we have a population that starts at time 0 and is 2,000, and it triples every 20 years. We'd like to figure out when it's going to be 9,000. And here we're asked for an exact answer and one correct to 3 decimal places, meaning you'll finally get to use your calculator if you've been waiting to do that. Now, of course, this is in the logarithmic function section, so we would expect that either this is a logarithmic function or its inverse, an exponential function. But how would we know that if it were just given it to us outside of this context? We've got something that's tripling every 20 years, meaning it's being multiplied by 3 every 20 years. That should remind us of constant percentage growth like we talked about when we did exponential functions. So before we can solve anything, we have to write our exponential function. And remember from last time that exponential functions take the form p0 times a to the t. p0 is the value at time 0, so that is 2,000. And we are tripling every 20 years. Tripling means you're multiplying by 3. So I'm going to put 3 as my, nope, just kidding. Don't want that equal sign yet. 2,000 is what we've got at time 0. We're tripling every 20 years. So we're multiplying by 3. Now, if I just put 3 to the t, how fast is this thing tripling? This, in fact, is tripling every year, right? Because when t equals 1, I've already got 6,000. So this is going much, much too fast. We talked last week about how to take care of that. We want to slow it down, so we make this t over 20. And now let's check. When I plug in 20 for t, what do I get? 3 to the 1. 3 to the 1 is 3 times 2,000 is 6,000. So it has tripled in exactly 20 years. But we want to figure out when it reaches 9,000. And again, I'd like us to get into the habit of checking in advance for what a reasonable answer is. So we already know that at time 20, we'll only be up to 6,000. So our answer had better be more than 20. Will it be more or less than 40? In 40 years, we should have tripled twice. So we should have gone from 2,000 to 6,000, and then tripled again to 18,000. So that's too much. So we know that the answer is going to have to be somewhere between 20 years and 40 years. Now we can forget all about the actual people in the problem and just go ahead and do the algebra. We've got a 2,000 and a 9,000. We can combine those together. Just divide by 2,000 on each side and get 9 halves. And I'm writing 9 halves. If you want to write 4.5, that's fine, of course. And now this is the sort of equation that we started off with in part A. We want to take the log of each side. So the ln of 3 to the t over 20 is the ln of 9 halves. Got to do the same thing to each side of the equation. We have our nice exponent rule, rule number 3, that lets us bring that exponent out front. T over 20 ln 3 equals ln of 9 halves. And now again, this is just a linear equation, so we just want to get t by itself. So we can multiply the 20 to the other side, divide the ln 3 to the other side. So t will be 20 ln 9 halves over ln 3. And that's our exact answer. Don't be tempted to do something crazy and cross off those ln's. There is no log rule that lets you do that. And since we were also asked for one correct to 3 decimal places, now you go ahead and put this into your calculator. And you should get, assuming I did this correctly, 27.381 years. And you notice that is in the range of what we expected it to be, right? We thought it had to be more than 20 years and not as much as 40 years. It had to be somewhere between 20 and 40, and that's what we get. And it's a good idea to try to plug this into your calculator all in one go. So for example, don't just put in ln of 9 halves and round that off to 3 decimal places and write that down on a piece of paper and then put that into the calculator times 20. Try to put the whole thing in, otherwise you might make some rounding error early in the problem that then causes you to miss some of the decimal places at the end. And we don't care whether you round or truncate, doesn't matter, it's all the same to us. All right, I hope that gives you a good understanding of logarithmic functions, the rules, the graphs, the properties and how to use them to solve equations, both with no context and with some context. And we have a check your understanding problem for you to go ahead and try now.